our paper titled VISH, does your smart home dialogue system also need training data? And I'm Mahda Noura, and I study my PhD at the Professorship of Distributed and Self-Organizing Systems at the Technical University of Chemnitz. This work was conducted in collaboration with my colleagues Sebastian Heil and Gaedke. So let's first start with an introduction of the topic. So in general, one of the main objectives of the Web of Things, and in particular the smart home, is to also enable end users to be able to control their smart devices to fulfill complex tasks. And these end users normally don't have technical experience or programming experience or even IoT device experience. And this is normally called end-user development. And to reach this objective, it is important that users can easily control and monitor their smart devices. One of the most popular ways for achieving this is through multimodal voice interfaces. You may be familiar with some of these personal assistants in the market, such as Amazon Alexa or Google Home. And you can see the normal process of such voice interfaces in this figure. So first, what happens is that the system receives the spoken utterances from the user as input. For example, it's too dark in this room. And then the voice input is then converted to a text form, and then a set of natural language processing technique is applied to identify the meaning of these user utterances. And finally, a suitable solution for the user goal is executed, which may of course also result in a set of device actuations. In our case here, the smart lamp could be turned on to improve the brightness, or as an equivalent, the shades could be opened. There is a big challenge in the process that I just discussed. The natural language processing unit needs a lot of sample data from the user to be able to understand and learn these user goals. Why do we need this? Because due to the complexity of natural language, and that basically humans express the same thing using diverse grammatical structures. Therefore, of course, this sample data cannot be arbitrary, and it should first of all represent the domain of smart home, and second of all be sufficiently large to enable the learning process. Because what we don't want is that when the user states a goal like open the door, then instead the shades are open, which of course decreases the user experience. Creating such a data set is not a trivial task, and it requires a large amount of smart home user utterances, which is representative of the goals that the user has. And it's a process that requires a huge manual effort. Let's look at this usual process for creating such a data set. So first, sample utterances are recorded from the user, and then they have to be transcribed to the equivalent text form. After that, the transcription is done. They have to be labeled with correct and meaningful entities to enable the learning process. Finally, the created dataset can then be fed into a natural language understanding model to train a model and provide a machine representation of the user utterances output. This process creates a high level of human effort to achieve sufficient quality necessary for natural language models, especially when the dataset grows in size due to the many recordings that is needed by diverse speakers. You need to do data cleansing, you need to transcribe each unique utterance, and of course the labeling process is also requires a lot of effort. Even if the transcription is done automatically, this is of course also error prone due to the inclusion of foreign words, multiple users speaking at the same time, different accents, background noise, and so on. Therefore, in this research paper, we propose a systematic method for generating a data set for in the smart home domain, which is based on speech recognition. Our approach follows a goal-oriented technique where the end user needs to state the desired goal or the effect that they are interested in, instead of stating the different device actions that need to be executed in order to fulfill this goal. So we define a goal-oriented Web of Things interface as a 5-tuple, which is in the form of a state transition system, where we also have the initial state of the environment and the goal state. And the device actions are basically what causes the transition, which leads you from one state to the other state. So, and every state is represented by a set of key value parameters, which is called the parameters. Like, for example, temperature equals 25. We have the parameter in this case called temperature, and the value 25. The device actions can, of course, have different effects on the physical environment when they are executed, and which are, in our case, in the Web of Things domain, they are basically a set of HTTP or MQTT requests. For example, the action of turning on the lamp could, the effect of turning on the lamp could be, of course, increase in the brightness, and it also could affect the power state of the lamp to change from a state of off to on. By looking at the existing work in the literature, we identified 3 different levels of utterances. They are device command, direct commands, and indirect goals. The difference between these 3 levels are the information that is specified by the end user. This level of information that is provided by the end user decreases as we reach the top of the pyramid. Let's look at the different layers. So device commands are basically strict commands given to a specific device. For example, turn on the heater. In this case, we have the action and we also have the device provided. And then we have direct goals. In direct goals, they do not explicitly specify the target device, such as increase the temperature. Here we don't have the device that is able to increase the temperature for us, but we only have the desired goal of the user, which is the temperature to be increased. And then on the most highest level, we have indirect goals, which even contain less information, and they form a goal-oriented mindset instead of speaking in terms of device commands, such as I'm freezing here or it's too cold here. In these goals, the end user basically states the overall desired effect rather than thinking in terms of individual devices or services that can satisfy the user goal. This is an overview of our proposed approach, which is called VISH, Voice Interface for Smart Home, which is a systematic method for generating a data set for the smart home that can be used for training different natural language understanding modules. As we already said, our solution follows a goal-oriented Web of Things interface that needs a state change in the physical environment. There are 2 actors involved in this process. We have a natural language engineer and the VISH toolchain, which supports the engineer to automatically generate the natural language utterances. As you can see, there are 7 steps in this process. In the first step, there is a set of goals collected from the end users, because any smart home will eventually be used by end users, and therefore it's crucial to understand how users would like to provide goals to their conversational systems. To realize this, we conducted an online survey with end users to collect the different goal samples in the scope of the smart home. In this process, we collected around 800 goals. And then in the second step, these goals were grouped into different categories based on the effect type, the parameters that were involved, or the specific device actions. And then for each category that was identified in step 2, the words or phrases that represented constant or variable information were identified. And therefore, from this, we identified a set of patterns in step 3. And these placeholders, they are basically a way to dynamically generate diverse utterances, which will be explained in the next steps. And then here in step 4, we have the grammar specification. So here you can see the WISH grammar. Each of the patterns that we identified in the previous step, they are represented using EBNF rules that specify the grammatical structure of utterances according to the pattern. All rules together form a context-free grammar called the WISH grammar. The WISH grammar has here represented as G, is basically a set of rules to automatically generate a set of natural language utterances in the smart home domain. With this grammar, we are able to build utterances like, could you activate the TV, or its synonym, turn on the TV. And then in the next step, we perform the labeling, and each rule in the WISH grammar contains certain smart home related information that of course needs to be identified and labeled for further steps. And these informations are in the natural language processing domains. They are called entities and intents. So let's have a look into these. Basically, entities are words or phrases that appear directly in the rule, and they span an individual word and needs to be therefore extracted from the utterance. To support the extraction process, what we did is that we marked these symbols in our WISH grammar, which they were representing the terminal symbols in the WISH grammar, sort of like the part of speech like tags. And in the WISH grammar, we support the following concepts which are extracted. We have devices, we extract actions, value, state, location, quantity. For example, in the first sentence, set the device, set the thermostat to 25 degrees. In this sentence, the action set will be marked, the thermostat as a device would be marked, the 25 as a value would be marked, and the degrees will be the unit of measurement. And on the other hand, we also label intents. Intents are not directly represented in the rule as placeholders, but they are basically the properties of the rule, and they span the whole utterance. And they can be identified through classification techniques. This requires us to label the generated utterances with classes that correspond to a physical parameter like temperature, humidity, brightness, air quality, and so on, or the effect type of an utterance will the effect that the user wants is an increase effect, or is it a decrease effect, or simply they want to assign a value to a parameter. And then the scope of the utterance, whether it's referring to a specific device or whether they want to change a parameter in the global scope, like increasing the brightness of the whole room. And then, of course, the goal type, whether the user utterance is of type device command, direct goal, or indirect. So then we have the next step, which is step 6, the utterance generation. And in this step, the WISH toolchain is applied to the grammar, and where it automatically generates all the possible utterances that can be provided according to our grammar. And it also, of course, includes automatically all the different entities that should be extracted, and all the different intents. So the output of our systematic approach is the VISH dataset. The dataset is large, and it consists of around 5 million labeled utterances for the smart home domain. In this table, you can see some of the characteristics of the generated dataset. Some characteristics are related to the smart home domain, for instance, the different device types, the different actions, the parameters, and some characteristics are related to the natural language domain itself, like the entities, their extractions, and so on. So, for example, here we have 305 different IoT device types in our data set, 130 different unique actions we have. And so our data set, the VISH data set, is publicly available. You can go to the link provided, and in the VISH data set you can download the data set, which provides also the labeling. We would like to now look at some of the existing work in this domain. So we have looked into the related work to identify the existing data sets in the literature in the smart home domain. This table shows a qualitative comparison between the selected data sets. Within the existing solutions, there are different approaches used for the dataset creation, such as collecting data from production system, like for example Google Home or Alexa. But the problem with these approaches is that the data is not publicly available for further research. And another group is performing controlled experiments in the smart home using microphones to record data sets from a limited number of users. And in this category, there are solutions like Dear Hub, Voice Home 2, Sweet Home, Athena. They basically do a set of experiments where the users have access to smart devices, and then they record the voice of the user to collect these utterances. And then we have the crowdsourcing method, which basically collects data from other users which are willing to help. And so our approach, however, our approach, as you saw, follows a generative grammar approach where we define a grammar, and then based on this grammar, the data set is generated automatically. So all the solutions stated here, they support device commands, and therefore the column device commands are excluded from this table. And however, as you can see, none of the existing work supports indirect goals. And so that's why when extracting the different parameters, or the effects, they don't extract or they don't consider these different concepts. And the WISH dataset includes 5 million unique utterances in the smart home domain, which is in English language, and it uses a generative grammar approach. We also evaluated the WISH dataset, and the objective of this experiment was to show the applicability of the generated WISH dataset for training different general purpose natural language understanding models. So in the next slides, we will see how this experiment was performed. So in order to evaluate the WISH dataset, we use the popular and open source natural language toolkit, which is called RASA. And within RASA, we use different natural language unit models and configurations to reduce the bias from this variable. You can see the procedure in the following. We initially had to do a set of data preparations where we transformed the generated data set to RASA's markdown syntax automatically using the WISH toolchain. And then in the next step, we did a data set division. While in standard evaluation methods that are performed in machine learning, they normally partition the training data set into training and holdout sets. So therefore, we separated the WISH training data set. 80% was used to train the different natural language unit models, and 20% was used as holdout and for testing purposes. And then we use the different NLU models in RASA, which basically differ in the way their intent classification or their entity extraction is performed. And the NLU models that we use are namely supervised embedding, pre-trained embedding convert, and pre-trained embedding spacing. Finally, a test was performed using the holdout set on the trained NLU models to calculate the quality in terms of accuracy, precision, and the F1 scored for both the intent classification and entity extraction. Here you can see an overview of the results of the NLU models for intent classification using the different NLU models and different epoch values. And with an increased number of epochs, you can see that the quality slightly increases, but it is also feasible to use the WISH dataset even with smaller number of epochs, which basically reduces the training effort that is required. And overall, you can see that the precision, recall, and the F1 of all the models that were tested and the different configurations are nearly equal to 1, which demonstrates that our WISH dataset is suitable for training the state-of-the-art NLU for smart home utterances. And here you can see the results of the NLU model using CRF model and SPACY for entity extraction techniques. You can see again the results show very comparable results for all the models and entities, and they are close to 1, which again shows that our WISH dataset is suitable for training the existing NLUs for entity extraction in the smart home utterances. Conclusion. And the results indicate that the WISH dataset can be successfully used to train the state-of-the-art NLU models for both intent classification and entity extraction. And the resulting quality is independent of the concrete NLU models that are used. And you can publicly access the dataset on the VSR homepage, and you can use it to train your custom NLU pipelines and to enhance this research in this domain. As future work, we intend to use the VISH dataset on a custom NLU pipeline to see how well the entity extraction and the intent classification is done. And we also intend to test this with goals received from end users in a live setting with smart home devices. And thank you very much for your attention. If you want to further contact me for more information regarding VISH dataset or the current research project regarding growth, I will be more than happy. And so please use the channel stated here. Thank you very much.